The navigation and flight management system of all modern airliners is based on the principle of inertial navigation. The inertial navigation system, which is usually abbreviated to INS or sometimes IN, began to be fitted to airliners in the late 1960s and early 70s. Those basic INSs have evolved into the more modern inertial reference systems. These are usually abbreviated to IRSs. Their technology and engineering has moved on 40 years, but the basic principles remain exactly the same as those of the early INS. INS is a complex and expensive full navigational aid. It is extremely accurate. It is independent of outside communications and ground stations. Consequently, it can operate worldwide. INS uses a sophisticated form of dead reckoning. It starts from a known position. It then measures and processes the accelerations of the aircraft. These accelerations give accurate data on speed and change of direction to determine a new position. In order to illustrate the principles of operation, we are going to look at 1970s style technology of INS. However, later lessons will develop these ideas to go on to the more modern IRS. INS measures or calculates the following navigational information: present position, that is, latitude and longitude; heading, which way the aircraft is pointing; track, the direction of the aircraft's path over the ground. The difference between heading and track is called drift. It is caused by crosswind. Ground speed, that is, the speed over the ground, which is usually not the same as the speed through the air. Again, this is the effect of wind. The INS also gives waypoint steering. This is the facility to enter a route as a series of latitudes and longitudes, and then have a steering signal generated to be displayed on the flight director system and fed to the autopilot. With waypoint steering, the INS will display the desired track between any two waypoints. For instance, the desired track between waypoint 1 and waypoint 2 in this example is 037 degrees true. It also calculates distance to go to the next waypoint and time to go. And it offers two other facilities, again, both associated with the desired track between two selected waypoints. The first is called cross-track displacement, and the second is track error angle. We'll explain these. This is a diagram of cross-track displacement. The INS has been programmed to steer the aircraft between waypoints 3 and 4. However, for some reason the IN has been disconnected from the autopilot and the aircraft has been flown out to the right of track, either manually or by taking a heading steer off the flight director. This could be, for instance, as a result of a mandatory air traffic control instruction. The INS can calculate the centre line of the route between the two waypoints and display the information that we are, in this case, 12.0 nautical miles to the right of the desired track. However, the word track can have another meaning. As well as being the path of the aircraft over the ground, it can also mean the direction of that path. Strictly speaking, this should be called track angle, but most people refer to it as just track. So, track error angle is not about whether you are a distance left or right of the desired track path. It is the difference between the desired track angle and the track angle you are flying at the time. Your actual track angle is the combination of your heading and your drift. If you are following the INS steer, the desired track angle and the actual track angle should be the same. However, If you have had to deviate from following the steers, again, possibly because of a mandatory air traffic control instruction, the two will not be the same. The difference is known as track error angle. In addition to all of these facilities, INS also generates roll and pitch data for attitude instruments. It is often assumed that the most important single advantage of INS over previous systems is that it produces a continuously computed present position with no dependence on external references. However, what is almost as important is that in order to compute this position, it was necessary to greatly improve heading measurement accuracy. INS heading is about 10 times more accurate than previous systems, which were gyromagnetic compasses. Additionally, INS heading is not dependent on Earth magnetism. INS calculates an initial true heading by detecting the Earth's spin, then relies entirely on high-grade gyros to maintain that accuracy. This will be explained later. INS can therefore be used for high latitude and polar navigation where the Earth's magnetic field may be weak, or the value of variation may be unreliable. There are 3 basic units in the INS. 2 of them are on the flight deck and are operated by the pilot. The third can be remotely located in the aircraft and does not have to be accessed in flight. The 2 components located on the flight deck are the Mode Selector Unit, often abbreviated to MSU, and the Control and Display Unit, often called the CDU. The third unit contains inertial sensors and reference devices. As we shall shortly see, these sensors are accelerometers and gyros. This box is called the Inertial Navigation Unit, which is often shortened to INU. We will now look at the principle of operation. When an aircraft flies, there are 3 effects of motion. These are position change, velocity, and acceleration. Of these, only one can be detected without external reference. You cannot measure position or velocity from equipment entirely contained within the aircraft, using no radio or radar, but you can measure acceleration. Imagine a pendulum with the weight concentrated in the bottom, mounted in an aircraft. If the aircraft accelerates, the weight swings backwards. If the aircraft decelerates, the weight swings forwards. However, we're using the words forwards and backwards in relation to the aircraft. But it is the aircraft which is changing its motion, not the pendulum. Let's go back to basics. The weight at the bottom of the pendulum is obeying Newton's first law of motion. Every body remains at rest or in uniform motion unless acted upon by an external force. Suppose that the weight and the aircraft are both travelling at 400 knots. Now the aircraft accelerates to 410 knots, but the pendulum weight, at least initially, remains at 400 knots. It appears to us that the weight is swinging backwards, but in fact the weight is maintaining uniform motion. The aircraft is accelerating ahead of it. The weight therefore has inertia, and we can use it to measure the acceleration. This is why it is called an inertial navigation system. The measuring device is called an accelerometer, and the acceleration it measures is with respect to inertial space, not local gravity. Newton's laws of motion are universal, not Earth-orientated. The measurement of acceleration would work even if gravity were not present. In fact, inertial navigation is used for spacecraft. Therefore, the acceleration, when suitably processed, gives a measurement of ground speed, not airspeed. By knowing where we were when we started and adding up how far we have gone, we can work out where we are now, rather like the odometer of a car. It is not enough to simply measure accelerations. They have to be converted, firstly, into velocities, and then, secondly, into distance gone, in order to find the new present position. Each of these processes is called integration. You will have already come across it if you have studied integral calculus previously. For INS, as we said, we have to integrate twice. First, to convert the accelerations into velocities. Secondly, to convert the velocities into distances. As pilots, we're not required to understand calculus. We simply need to know that there are electronic devices that can carry out these processes for us. They're called integrators, and they are used in INS. This is a diagram of a Miller integrator, which was used in the 70s and is from the period of the equipment that we are looking at. However, these days it will be done digitally. Let's summarize what we've covered so far. INS is a complex and expensive full navigational aid. It is extremely accurate, independent of outside communications and ground stations, and can operate worldwide. INS provides much more than just present position. All of these facilities are measured or calculated. INS heading is about 10 times more accurate than previous gyromagnetic compass systems and is not dependent on Earth magnetism. It can therefore be used for high latitude and polar navigation, where the Earth's magnetic field may be weak or the value of variation may be unreliable. The basic units of the INS are the Mode Selector Unit, or MSU, the Control and Display Unit, or CDU, and the Inertial Navigation Unit, or INU. Accelerometers measure accelerations, which are integrated first into velocities, then into distance gone. By knowing where we were when we started and adding up how far we've gone, we can work out where we are now.